first nuclear bomb was exploded at the Alamogordo bombing range in New Mexico in the United States. The bomb was the child of J. Robert Oppenheimer, who had been appointed head of the top-secret Manhattan Project just 28 months earlier. After recruiting what General Leslie Groves called the greatest collection of eggheads ever, including 3 past and 7 future Nobel Prize winners, Oppenheimer organized the largest and most sophisticated technological project in human history up to that time. As an undergraduate at Harvard, Oppenheimer had taken an elective in Indian philosophy. And on the morning of July 16, 1945, as the flash of intense white light faded and the purplish fireball rose, sucking desert sand and debris into a mushroom cloud more than 7.5 miles high, Oppenheimer quoted from Hindu scripture, "I am become death," he said, "the shatterer of worlds." Oppenheimer's misgivings about the nuclear bomb spread after World War II. And he wasn't alone. In the post-war years, a growing number of people came to share Oppenheimer's doubts about the bomb specifically and technology in general. Increasingly, people began to think of technology as a monster run amok, a Frankenstein more than a savior. The idea spread especially quickly in the 1970s and 1980s, when a series of big technological disasters woke many people up to the fact that technological advance is not always beneficial and not always even benign. You may have heard about the 1984 gas leak at the Dow chemical plant in Bhopal, India, which killed 14,000 people. The explosion of the number 4 nuclear reactor at Chernobyl, Ukraine in 1986, which released 30 to 40 times more radioactivity than the nuclear blast of Hiroshima, killing 10,000 people. You may have heard, too, about the running aground in 1989 of the oil tanker Exxon Valdez off the coast of Alaska, the oil slip from which killed hundreds of thousands of animals. Facing a whole series of such events in the 1970s and 1980s, one sociologist, Charles Perrow, P-E-R-R-O-W, from Yale University, coined an interesting term, normal accidents. Normal accidents, said Perrow, are mishaps that occur because the very complexity of modern technologies ensures that those technologies will inevitably fail, although in unpredictable ways. For example, any large computer program, say the operating system of your personal computer or your Mac, contains many thousands of conditional statements. They take the form of if X equals Y, do Z, and if A equals B, do C. As a result of these many thousands of statements in a program, they may take on billions of different combinations when the program is actually running. So complex programs like the operating system of your PC or Mac cannot be tested for all possible eventualities. Sometimes combinations of circumstances come into play that weren't anticipated by the programs. And when those rare combinations of circumstances occur in a program, they have unforeseen consequences that are usually minor, occasionally amusing, sometimes expensive, and too often dangerous. For example, an fairly amusing one occurred in the early 1990s when the avionics system for the F-18 bomber was programmed, and inadvertently the program caused the bomber to flip upside down every time it crossed the equator. They quickly solved that problem. But you've experienced normal accidents whenever you're computer crashes or hangs. That is precisely the emergence of certain conditions that weren't anticipated by the original programmers and that come into play when complex combinations of conditional statements are realized. German sociologist Ulrich Beck, B-E-C-K, also coined a term in the 80s that stuck when he said that we live in a risk society. What did he mean by a risk society? Well, he meant we live in a social system in which technology distributes danger and advantage among all social groups, although some groups are more exposed than others are. But what he wanted to emphasize by this term was the notion that the society in which we live is, above all else, a society that is full of risk. Moreover, he said, in a risk society such as ours, danger doesn't result from normal accidents alone. In addition, increasingly, risk exists because of mounting environmental threats. Now, environmental threats are different from technological threats, insofar as they are more widespread, that is to say, they affect many more people. The Chernobyl nuclear disaster affected people in parts of Ukraine and Belarus, and to a much lesser degree in other parts of Europe. That's about it. But environmental threats tend to be global in scope. Moreover, they are chronic, they are not episodic. They tend to exist not in brief episodes of time, brief meaning 5 minutes or 5 years. Rather, they are long-term, lasting decades, if not centuries. And they are more ambiguous than technological accidents, or even more ambiguous than natural disasters. We all have a pretty good sense of what we need to do if the river floods or if the electricity goes out. We have contingency plans for that. But environmental threats like global warming, about which I'm going to talk at some length today, are much more ambiguous, and our plans for dealing with it are much less clear. Therefore, environmental threats, because they are chronic, because they are extended over a much longer period of time than mere technological threats, and because they are ambiguous, they cause a lot more stress than a flood or an electrical outage. That stress is spread over a longer time, and we are less sure what to do about it, and therefore stress over environmental issues tends to be greater. New and frightening terms have entered our vocabulary: the greenhouse effect, global warming, acid rain, ozone depletion, endangered species, ocean acidification. So, to many people, technology now seems to be spinning out of control. From their point of view, technology does indeed enable the production of more and more goods and services, but at the cost of normal weather patterns, breathable air, drinkable water, safe sunlight, and plant and animal diversity. Now, these considerations raise the two tough questions I'm going to be asking with you this afternoon. First, what is the most dangerous consequence of technology? And how is risk from this technological spin-off distributed among various social groups? I'm going to focus on global warming, showing that while it puts all of humanity at risk, the degree to which people are at risk varies by class, by race, by country of residence. We're all at risk. Some people are more at risk than others. In brief, I'm going to try to demonstrate that the socially and economically advantaged people, disadvantaged people of the world are the ones who are most at risk. And the second question I'm going to raise is this: how can we overcome the dangers of global warming? I'm going to argue that we have a number of solutions that have been proposed, and that two of those solutions, the market and technological solutions, while getting us part of the way to answering the problem of global warming, are insufficient by themselves. In addition to market and technological solutions, I'm going to argue that we need a lot of self-sacrifice and cooperation. Well, I hope you'll allow me to begin by quickly reviewing, for those of you who don't know, what we mean by global warming. I made a picture, an animation actually, in order to explain this to you very briefly. Ever since the Industrial Revolution, humans have been burning increasing quantities of fossil fuels, by which I mean coal and oil and gasoline, natural gas, and so forth. We've done so to drive our engines, our cars, our furnaces, our factories. And when we burn those fuels, these fossil fuels, they release carbon dioxide and other heat-trapping gases into the atmosphere. Picture one. So we burn these fossil fuels, and certain gases are released into the atmosphere, in particular carbon dioxide and methane. It's not the only source of heat-trapping gases, but it has become a major source of heat-trapping gases in the atmosphere since the time of the Industrial Revolution in the late 18th century. Pardon me. The accumulation of these heat-trapping gases allows more solar radiation to enter the atmosphere and less heat to escape. This is the so-called greenhouse effect. Most scientists, most climate scientists believe that the greenhouse effect contributes to global warming, a gradual increase in the world's surface temperature. So more heat enters the atmosphere than escapes, because some of it's absorbed into the land and the water, and some of it is reflected back by the blanket of heat-trapping gases. Stage number 3 in this process. Warming melts ice, and it creates more water as a result. It also reveals tundra, which are areas of land above the tree line that are covered by grass, moss, shrubs, and the like. So here's stage 3. Ice melts, more water is created, tundra is revealed in northern reaches that were formerly covered by ice. Now, tundra contains rotting vegetation and animal remains. This is land that was formerly covered by ice for many thousands of years. When the ice disappears, you've got, in addition to the vegetation, rotting vegetation and animal corpses. And that rotting releases methane into the atmosphere. Methane is another heat-trapping gas. In fact, as a heat-trapping gas, it is 21 times more effective than carbon dioxide is. It has a shorter life. Methane, when it's released, stays in the atmosphere for 12 years. Carbon dioxide stays in the atmosphere anywhere from 50 to 200 years. But it's 21 times more efficient or effective in trapping heat than carbon dioxide is. Meanwhile, the new water from melted ice reflects heat less than the ice did, because water is darker than ice. So it speeds up global warming. So this then is how global warming takes place. And here is a graph which shows you the change in global surface air temperature and the concentration of carbon dioxide in the atmosphere between 1880 and 2009. In black, we have temperature measurements from the NASA Goddard Space Institute. And in red, we have carbon dioxide concentration measurements. You'll notice that both trend upwards. And you'll notice also that until about 1960, looking at both of those lines, there wasn't much of a trend. There was a slight upward trend, but it was very slow. But around about 1960, 1970, the curves, there's an inflection point, and the curves become steeper. That is to say, the rate of global warming starts to increase much more quickly, as does the level of concentration of carbon dioxide in the atmosphere. Some people consider that the safe upper limit for carbon dioxide in the atmosphere is 350 parts per million. We already exceed that so-called safe limit. I have another illustration. This time I need to go to a website in order to pull it off. This is a NASA website. Just give me a moment here. Working for me. Oh, I see. How do you like that? You'll have to do this at home. Go to that website, and what you'll see is a really nice animation which shows you for each 5-year period since 1880, between 1880 and 2012, how the entire planet has warmed. It divides the world into various sections. It says that the period from 1951 to 1980, it takes that as the base, and it asks what are the deviations from the average temperature between 1951 and 1980 for each 5-year period from 1880 to 2012. And it's color-coded in various parts of the world. And what happens in this animation is you see that it goes from frigid blue to a warmer blue to a light yellow to a dark yellow and then to an orange and then to red in many parts of the world, especially in the northern hemisphere. So we see this quite striking change in the degree of global warming over this period. So please, this website address is available, and I encourage you to take a look at it when you get back home. Let me try my final animation, and we'll hope it works. You can see here one of the consequences of global warming, I hope. It shows you the consequences of global warming for ice in the polar ice in the Arctic ice cap. Just over a 5-year period from 2003 to 2007. So pretend you're in a satellite looking down at the North Pole. This is what you would see in the summertime. You see ice covering the Arctic Sea. The dotted area shows you the area that was permanently, or it's regarded as the permanent ice cap, that hasn't changed, that hasn't thawed in many thousands of years. So this is the size of the ice cap here in 2003. In 2004, it looks like this. 2005, like this. 2006, like this. And 2007, it gets so small that the so-called permanent area of frozen ice cap does not exist in part. Most climate scientists believe that as early as 2050, we will have reached the point that there will be no summer ice in the far north. It will be completely open to navigation, of course, resulting in a huge increase in the amount of water and increased decreased reflectivity and greater heat absorption on the part of the planet. Now, what are some of the consequences of this global warming that I've sketched here? Well, first of all, as more water evaporates, it causes more rainfall and bigger storms. That's one big important consequence of global warming. Secondly, with more rainfall and bigger storms, more flooding takes place, more soil erosion, so less land is available for cultivation, and there is more famine in the world. Third, with more global warming comes more drought. That is, periods when there is not enough water for crops and even for people in certain areas. Again, that means less cultivable land and more famine. Fourth, oceans rise because warm water expands and because the melting of the polar ice caps puts more water in the oceans. The result is more frequent and heavier flooding of heavily populated coastal regions. The Nile Delta in Egypt, Bangladesh, New York City, most recently. All of these are places that are experiencing floods, huge floods, that are extremely rare in human history. Moreover, some low-lying populated islands in the South Pacific in particular are experiencing complete coverage by the ocean. The ocean's rising, and as the ocean rises, these islands are threatened with complete coverage. There are already population movements from some of these islands to Australia and New Zealand as people realize that they have no future on these little plots of land. The final consequence of global warming that I will mention is ocean acidification, and then we'll get back to sociology. Ocean acidification. Given increased carbon dioxide in the atmosphere, the oceans absorb some of that carbon dioxide, creating carbonic acid. In other words, the pH of the oceans decreases. They become more acidic, and they're becoming more acidic more quickly than they have been at any point in the past 300 million years. For example, scientists tell us that 56 million years ago, ocean pH fell. The oceans became more acidic by 0.01 units per century. The pH scale is a 14-point scale, right? So it was falling, becoming more acidic by 0.01 of those 14 units per century. Now, however, pH is falling by 0.1 unit per century. So the rate of acidification has gone up tenfold over the past 56 million years. What does this do? It means that plant life, fish life, entire species are threatened by ocean acidification. Certain species can't live with increased acidity in the ocean. Now, one way of looking at the consequence of global warming, such as I've described, is by looking at how much money insurance companies pay out worldwide over given periods of time due to so-called natural and human catastrophes. Why do I put natural in quotation marks? Because I've been arguing that natural occurrences, like floods and storms and so on, are not entirely natural. They are also accelerated by, made more intense by human action, namely by the burning of fossil fuels. So what this graph does is it takes total payouts by insurance companies worldwide for natural and human catastrophes in 3 time periods: 1970 to 86, 87 to 2003, 2004 to 2009. What does the graph say? What does it scream? It screams that payouts are increasing very, very quickly. They tripled from the first time period to the second, then they doubled from the second to the third time period. Way, way above the rate of inflation. What's happening is that natural and human catastrophes are becoming bigger and bigger, and more insurance money is being paid out as a result. Of course, this doesn't really reflect the natural and human catastrophes that occur in many of the less developed countries, because most of the payouts by insurance companies are payouts to relatively well-to-do countries and relatively well-to-do people in those countries. People in Bangladesh who experience a typhoon or a flood don't have insurance. They don't get paid out by insurance companies. Their suffering is not reflected in these figures. The suffering of people in New York who went through that big flood last year, that is reflected here. Okay, but this is only a partial indicator then. And another way of looking at the magnitude of the problem we face is this last graph in this series. And I need to explain it in order to have it make sense to you. Most climate scientists agree that if we experience an increase in the mean surface temperature of 2 degrees Celsius or more, the results are going to be catastrophic, far worse than they are now. Until now, we have experienced, since the Industrial Revolution, an increase of 0.81 degrees Celsius on average in surface temperature. If we experience 2 degrees, we're in for really catastrophic trouble. Well, recently, a group of climate scientists and statisticians in Germany and the United Kingdom wrote a paper in which they did some extremely interesting calculations that climate scientists worldwide have almost unanimously accepted as valid. What they did, first of all, was they figured out how much we got in reserves of fossil fuel in the world. How many proven reserves of coal, oil, and natural gas do we have? And they calculated we have enough proven coal, oil, and gas reserves so that if it were all burned off, it would produce 2,795 billion tons of carbon dioxide. Okay? That's the first idea, the first finding of their paper. If we burned off all the proven reserves of fossil fuels, these 3 fossil fuels, we would have produced almost 2.8 billion tons of carbon dioxide. Now, also, they wanted to know how much of that could be burned off and still have us reduce the chance of not going above an increase of 2 degrees Celsius in temperature. If we could reduce the chance of going no higher than that to 20%. In other words, right now we have a certain probability of going over the 2% limit that would cause catastrophic damage to the planet. It would be a good idea, they argue, credibly, if we could reduce the chance of going to the 2% level or higher, if we could reduce that chance to the 20% level. So how much fossil fuel can we burn and simultaneously reduce the chance of not reaching that 2 degree level to 20%? And the answer is given in this graph. They said that we can, if we burn just 32% of these fossil fuels, approximately 1/3 by 2050, then we'll be okay. We will reduce the chance of exceeding that 2 degree global warming limit to 20% if we burn just 1/3 of that fuel. However, there's a problem. At current consumption rates, we will have burned up that 32% of our reserves by the year 2024. In other words, in just 11 years from now, we will have burned up 32% of all fossil fuels. So it will be no longer possible for us at that point to reduce to 20% the chance of keeping global warming to 2 degrees Celsius or below. In other words, if we keep on doing what we have been doing in terms of burning fossil